19 pilots died testing this aircraft before it ever saw combat. The engine leaked poison into the cockpit. The tail ripped away without warning during dives. Senior commanders wanted to cancel the entire program and melt the airframes for scrap. Yet by the summer of 1944, German soldiers had a name for the sound these machines made as they screamed down from the sky. They called it Jabo-Schreck, fighter-bomber terror. This is the story of the Hawker Typhoon and the 3-inch rocket that turned a failed interceptor into the most feared ground attack aircraft of the Second World War. And it begins not with triumph but with disaster. On the morning of 9th of May 1940, test pilot Philip Lucas climbed into the cockpit of the first Typhoon prototype at Langley Aerodrome. The aircraft beneath him represented everything British aviation hoped to achieve: a fighter capable of 400 miles per hour, armed with 12 machine guns, powered by the most advanced engine ever fitted to a single-seat aircraft. 20 minutes into the flight, Lucas heard a sound no pilot ever wants to hear, a crack, then another. He looked over his shoulder and saw daylight where there should have been metal. The rear fuselage was tearing itself apart. Most pilots would have abandoned the aircraft immediately. Lucas was not most pilots. He nursed the crippled prototype back to Earth, landing with the tail section barely attached. The subsequent investigation revealed a design flaw so fundamental that it would kill 19 more men before engineers found a solution. The Typhoon should never have survived. It should have been abandoned in 1941 when carbon monoxide from the Napier Sabre engine began seeping into cockpits, forcing pilots to wear oxygen masks from the moment they started the engine until they shut it down. It should have been scrapped in 1942 when 3 aircraft in a single month suffered catastrophic tail failures during high-speed dives. It should have been forgotten when Fighter Command's own assessment concluded that the aircraft was unsuitable for its intended role as a high-altitude interceptor. Instead, something remarkable happened. The men who flew the Typhoon refused to give up on it. They saw what the aircraft could do at low altitude, how the massive Napier Sabre engine delivered power that no other fighter could match below 5,000 feet. They watched the Typhoon catch Focke-Wulf 190s that had been terrorizing coastal towns with impunity. They understood that hidden within this troubled machine was a weapon waiting to be discovered. What they could not yet imagine was the device that would transform the Typhoon from a problematic fighter into a legend. A weapon so simple that German intelligence initially dismissed it as propaganda. A weapon that would kill more enemy armor than any tank gun in the Allied arsenal. The rocket projectile Mark III, 60 pounds of British engineering that changed warfare forever. By the spring of 1942, RAF planners confronted an uncomfortable truth. The Allied air forces could reach almost any target in occupied Europe, but once they got there, they often couldn't do much about it. Heavy bombers carried enormous payloads, but couldn't hit anything smaller than a city block with reliable accuracy. Medium bombers required clear weather and multiple passes, making them vulnerable to anti-aircraft fire. Fighters could strafe with cannon and machine guns, but 20mm shells simply bounced off the armoured vehicles and fortified positions that protected German supply lines. The Tiger tank illustrated the problem perfectly. This 57-ton monster had appeared in North Africa in late 1942, and nothing in the RAF's fighter arsenal could touch it. The armour that protected its crew was designed to withstand direct hits from anti-tank guns. Cannon shells from attacking aircraft made spectacular sparks and accomplished nothing else. Bombs offered theoretical solutions, but practical nightmares. A fighter diving to release bombs had perhaps 3 seconds to align the attack before pulling up to avoid the ground. In those 3 seconds, a pilot had to judge airspeed, dive angle, altitude, wind drift, and release point, while being shot at from every direction. Miss by 50 yards, and you'd done nothing but waste ordnance. Miss by less than 50 yards, and you might fly through your own explosion. The Royal Navy had already found a partial answer. Since 1941, Coastal Command aircraft had been using rockets against U-boats in the Bay of Biscay with encouraging results. These unguided projectiles were inaccurate, certainly, but they carried enough explosive to damage a submarine's pressure hull. And unlike depth charges, they could be launched from a safe distance, rather than requiring the aircraft to fly directly over its target. What worked against submarines, the thinking went, might work against tanks. The challenge was adapting a naval weapon for use against fast-moving ground targets. A U-boat on the surface was essentially stationary. A Tiger tank advancing across a battlefield might be moving at 30 miles per hour whilst firing at the approaching aircraft. The engagement geometry was entirely different. British ordnance engineers at the Projectile Development Establishment began working on the problem in mid-1942. Their objective was straightforward: create a rocket that could be carried by a single-engine fighter launched from a dive and powerful enough to destroy any armoured vehicle in the German inventory. The result would become the most effective air-to-ground weapon of the entire war. The rocket projectile Mark III, RP-3 for short, embodied a design philosophy that would have horrified precision engineers but delighted infantrymen. It was crude, inaccurate, and devastatingly effective. The basic assembly comprised two components bolted together: a 3-inch diameter rocket motor and a detachable warhead. The motor used solid cordite propellant, the same material that had been launching artillery shells for decades, packed into a steel tube with 4 small fins welded to the rear for stability. Ignition came from an electrical squib connected to a firing button in the cockpit. Press the button, current flows through the cable, the squib sparks. 19 pounds of cordite begins burning, and 1.6 seconds later, the complete assembly is travelling at roughly 450 miles per hour relative to the launching aircraft. Simple engineering, spectacular violence. The warhead options told you everything about what the RAF expected these rockets to hit. The original 25-pound solid armour-piercing head was designed for penetrating tank armour. It worked reasonably well against lighter vehicles, but proved disappointing against Tigers, whose thick hides simply deflected the relatively small projectile. The solution came from an unexpected direction. Royal artillery gunners in North Africa had discovered that high-explosive shells from their 25-pounder field guns were actually more effective against tanks than dedicated armour-piercing rounds. The explosive shock didn't need to penetrate the armour completely. It simply had to transmit enough force through the steel plate to kill or incapacitate the crew inside. Applying this principle, engineers developed a new 60-pound semi-armour-piercing warhead. The nose cone was hardened to penetrate lighter protection, but behind it sat 11 pounds of Amatol high explosive. This warhead didn't need to punch through a Tiger's frontal armour. If it struck the thinner deck plating or found a vulnerable point like the engine compartment or track assembly, the resulting explosion was devastating. Even near misses could strip track links, shatter vision blocks, or kill exposed crewmen with shrapnel. The mounting system was equally straightforward. 4 launching rails bolted under each wing, angled slightly downward to compensate for the Typhoon's attack dive angle. Spring clips held each rocket in place until firing. A selector switch in the cockpit allowed pilots to launch rockets singly, in pairs, or as a complete salvo of 8. Most chose the full salvo. When you only had seconds to engage a target, there wasn't time to fire and adjust. Manufacturing the RP-3 became an industrial challenge of its own. Amatol filling was hazardous work, and several factories suffered explosions during production. The propellant mills that produced cordite operated around the clock. Steel foundries forged warhead casings to specifications that demanded precision whilst accepting no delays. By late 1943, British factories were delivering more than 50,000 rockets per month, a production rate that would sustain 26 Typhoon squadrons through the most intensive combat operations of the entire war. Each rocket cost approximately £12 to manufacture. A Tiger tank cost roughly 100,000 Reichsmarks. Even accounting for missed shots, the economics strongly favoured the rockets. The marriage of aircraft and weapon happened almost by accident. Through 1942 and into 1943, the Typhoon had struggled to find its purpose. Too unreliable for sustained operations, too sluggish at altitude for interception duties, too dangerous to its own pilots to inspire confidence. Fighter Command was genuinely considering cancellation when the aircraft began appearing in a role nobody had originally planned. Low-level intruder operations over occupied France revealed something the performance charts hadn't predicted. Below 5,000 feet, where the thick air let the Napier Sabre engine breathe properly, the Typhoon was brutally fast. Those thick wings that created compressibility problems at altitude provided a stable platform for strafing runs, and the airframe's sheer strength, initially a liability because of the weight penalty, meant Typhoons could absorb battle damage that would have destroyed lighter fighters. Squadron leader Roland Biemont of 609 Squadron became the aircraft's most influential advocate. A former Hurricane pilot who had flown through the Battle of Britain, Biemont understood what ground forces needed from air support. When he took command of 609 Squadron in late 1942, he began developing tactics that would eventually revolutionize close air support. The key insight was that the Typhoon's weaknesses as a fighter were actually strengths for ground attack. The heavy weight that reduced maneuverability meant the aircraft held rock steady during diving attacks. The powerful engine that consumed fuel at alarming rates also provided the acceleration to escape from concentrated anti-aircraft fire. Even the troublesome carbon monoxide problem became manageable once pilots learned to fly with oxygen from takeoff to landing. When rocket rails arrived in late 1943, everything changed. Fitting the RP-3 required significant modifications to the Typhoon airframe. Each wing had to support 4 launching rails plus 4 loaded rockets, an additional 240 pounds per side. Structural engineers reinforced the wing spars at the attachment points. Electricians routed firing circuits through the wing cavities. Armourers developed loading procedures that could reload a complete aircraft in under 20 minutes. The modified aircraft, unofficially called Rocketfoons, alongside the earlier Bombfoons, entered operational service with 181 Squadron in September 1943. First combat launches came the following month. Initial results were encouraging but imprecise. Pilots were still learning how to aim an unguided rocket from a diving aircraft travelling at 350 miles per hour. What emerged from those early operations was a targeting technique unlike anything previously attempted. Forget precision, embrace saturation. A single Typhoon firing 8 rockets in a half-second ripple created a pattern roughly 30 yards across at typical combat ranges. 4 aircraft attacking in sequence delivered 32 warheads onto the same general area within a minute. Against concentrated enemy positions, a convoy, a troop assembly, a defended crossroads, the effect was less like an air attack and more like a naval broadside. The Typhoon's firepower, commanders began to realize, was equivalent to a destroyer's main armament, and destroyers couldn't fly 200 miles inland. Traditional close air support operated on a model designed for static warfare. Ground forces identified targets. Requests filtered up through brigade, division, and corps headquarters. Eventually, sometimes hours later, the Air Force dispatched aircraft to attack positions the enemy had long since vacated. This system was worse than useless. It was actively wasteful. Aircraft burned fuel attacking empty fields, whilst German units moved freely elsewhere. Air Vice Marshal Harry Broadhurst commanding 83 Group of the 2nd Tactical Air Force, had seen the problem firsthand in North Africa. There, the Desert Air Force had experimented with something called the Tentacle System, mobile radio units that could communicate directly with aircraft overhead. The results had been promising. What Broadhurst proposed for the Normandy campaign was more radical still. The concept borrowed its name from London taxi stands. Aircraft would orbit designated points above the battlefield, cab ranks, awaiting calls from forward air controllers embedded with ground units. When a target appeared, the controller would talk the pilots directly onto it using landmarks visible from the air. No paperwork, no delays. A tank company commander watching enemy armor approach his position could have rockets falling on those tanks within minutes of requesting assistance. Implementing this system required solving problems that peacetime planners had never considered. VHF radios operated line of sight only. Controllers on the ground could not reliably communicate with aircraft more than a few thousand feet above them due to terrain interference. This meant Typhoons in the cab rank had to orbit at uncomfortably low altitudes, 3,000 to 4,000 feet, well within range of German anti-aircraft guns. Controllers had to learn a new vocabulary. Describing targets using map coordinates was useless when pilots needed to identify features in seconds whilst flying at 300 miles per hour. Instead, controllers spoke in landmarks. Target is the farmhouse with the red roof, 200 yards east of the crossroads. Enemy armor concealed in the orchard immediately north. Pilots developed an almost instinctive understanding of what ground features looked like from attack altitude. Artillery liaison became critical. The fastest way to mark a target was with smoke shells. A controller could direct artillery to drop smoke onto enemy positions, then talk Typhoon pilots onto the rising column. This required coordination between air and ground forces that had never existed before. Royal Artillery gun crews taking orders from RAF personnel whilst both worked to support Army units in contact with the enemy. The human element proved as challenging as the technical problems. Forward air controllers were typically pilots themselves, men who understood both what aircraft could do and what ground forces needed. They worked from armoured vehicles equipped with multiple radio sets, aircraft frequencies, artillery frequencies, ground force frequencies, juggling simultaneous conversations whilst bullets cracked overhead. These controllers accepted extraordinary risks. Their job required them to operate at the forward edge of battle, often within machine gun range of enemy positions. Several were killed or captured during the Normandy campaign. The survivors developed an almost telepathic relationship with the pilots they directed, each learning to anticipate what the other needed. The cab rank system that emerged was, in military terms, a revolution. For the first time in history, ground commanders could call down devastating airstrikes within minutes of identifying targets. The German army, accustomed to operating under skies controlled by the Luftwaffe, found itself suddenly and terribly vulnerable. The Typhoon squadrons that deployed to France in the summer of 1944 faced combat of an intensity that even veterans found shocking. By D-Day, the 2nd Tactical Air Force had 18 operational squadrons of Typhoon IBs, roughly 200 aircraft, with another 9 squadrons in fighter command providing reinforcement. These units would fly more sorties, suffer more casualties, and claim more enemy equipment destroyed than any comparable force in military history. The bocage, that dense hedgerow country of Normandy, created tactical conditions that perfectly suited rocket-armed Typhoons. German armour concealed in the maze of small fields and sunken lanes was virtually immune to artillery observation. But from the air, the distinctive shapes of tanks and self-propelled guns were clearly visible against the summer greenery. A controller on the ground might have no idea where enemy armour was hiding. A Typhoon pilot at 2,000 feet could see the telltale tracks and crushed hedges that revealed German positions. The first major test came during Operation Goodwood in July 1944, the British attempt to break through German defences east of Caen. 3 armoured divisions attacked across open ground towards the Bourgebus Ridge, running straight into prepared positions manned by the 21st Panzer Division and the elite troops of the 1st SS Panzer Division Leibstandarte. What followed was the largest tank battle the British Army had ever fought. Typhoon squadrons flew continuously throughout the 3 days of Goodwood, attacking any German armour that revealed itself. Pilots claimed more than 200 tanks destroyed, an extraordinary figure that would later be revised substantially downward when operational research teams examined the battlefield. The actual number of tanks killed by rocket strikes alone was closer to 10. This disparity between claims and confirmed kills sparked controversy that persists to this day. Critics pointed to the figures as evidence that rockets were ineffective. Defenders argued that the numbers missed the point entirely. Consider what actually happened when a German tank crew spotted Typhoons rolling into an attack dive. First, the psychological effect. Men who had survived artillery barrages and tank engagements came apart psychologically when rockets started falling. The random nature of area weapons, you might survive whilst the man next to you was vaporized, created terror that conventional bombardment did not. Prisoners taken after rocket attacks described paralyzing fear that made rational action impossible. Second, the disruption. A tank that reversed into a hedgerow to escape air attack wasn't supporting the infantry defence. A convoy that scattered off the road wasn't delivering ammunition to the front line. German commanders found their units constantly dispersing, constantly hiding, constantly looking skyward instead of fighting the battle in front of them. Third, the abandonment. Operational research teams found dozens of German tanks and assault guns that had been abandoned intact or with only superficial damage. Their crews had fled after rocket attacks, convinced their vehicles were death traps. A Tiger that had cost months of industrial effort to build was worthless if its crew wouldn't climb inside. The true measure of the Typhoon's effectiveness wasn't tanks destroyed per rocket fired. It was the degree to which German armoured forces ceased to function as coherent units under sustained air attack. By that standard, the rockets were devastating. The road from Troon to Chambois measured less than 5 miles. In August 1944, it became the most dangerous stretch of ground in Western Europe. Following the American breakout from Saint-Lô and the failed German counterattack at Mortain, the remnants of 2 German armies, the 7th Army and the 5th Panzer Army, found themselves trapped in a pocket centred on the Norman town of Falaise. Perhaps 80,000 men with hundreds of tanks, thousands of vehicles, and tens of thousands of horses were squeezed into a shrinking perimeter whilst Allied forces closed the escape routes. By the 15th of August, only one significant gap remained. The road through Chambois offered the last possibility of escape for units that had not already been destroyed or captured. Every German formation still capable of movement converged on that single corridor. For the Typhoon squadrons of 2nd TAF, this was the target of a lifetime. Wing Commander Charles Green, leading 123 Wing from a forward airstrip near Bayeux, assessed the reconnaissance reports on the morning of the 17th and realized that standard tactics would be insufficient. With enemy vehicles packed bumper to bumper along narrow Norman lanes, individual attacks would accomplish nothing before darkness allowed dispersal. Green ordered mass formation strikes, entire squadrons attacking simultaneously rather than the usual 4 aircraft flights. What followed over the next 4 days defies easy description. Typhoons took off from forward strips with full rocket loads, flew perhaps 15 minutes to reach the pocket, expended their ordnance in a single devastating pass, and returned for rearming. Some pilots flew 6 sorties in a single day. Ground crews manhandled rockets onto wing rails in a continuous cycle of loading, launching, and reloading that pushed men and machines to their limits. Flight Lieutenant Herbert Pring of 181 Squadron later described his third attack on the 17th of August. By that point, smoke from burning vehicles had become so dense that he selected targets purely by thermal signature, bright spots indicating engine blocks still radiating heat. His salvo struck a Panther tank attempting to escape across open ground. 2 rockets hit the turret ring, whilst a third penetrated the rear deck. The tank continued rolling for another 30 yards before catastrophically exploding, the turret cartwheeling through the air in a pillar of flame that Pring could see from his pull-out altitude. By his 4th sortie that day, Pring said, he could no longer distinguish individual vehicles. The entire corridor had merged into one continuous fire. German survivors left accounts that corroborate the devastation from below. Hauptmann Erich von Luck, commanding a Kampfgruppe from 21st Panzer Division, recorded that rocket attacks made organized movement impossible after midday on the 17th. His Tigers, nearly impervious to Allied anti-tank guns, proved helpless against warheads striking from above. 1 rocket penetrated his command tank's engine deck, igniting fuel and ammunition simultaneously. Von Luck escaped through the driver's hatch seconds before internal explosions blew the turret 50 feet from the hull. The scene that greeted Allied forces when they finally closed the gap defied belief. An estimated 10,000 vehicles had been destroyed or abandoned. Perhaps 50,000 German soldiers had been killed, wounded, or captured. 5,000 horses lay dead in harness along roads so clogged with wreckage that tanks could not pass. General Eisenhower visited the battlefield shortly after its capture and later wrote that it could only be described by Dante. The stench of death overwhelming, the scale of destruction incomprehensible. The Falaise Pocket broke the German army in the west. The formations that escaped did so without their heavy equipment, without their transport, often without their weapons. They would never recover sufficiently to mount another major offensive in France. And more than any other weapon system, the Typhoon and its rockets had made that victory possible. If Falaise demonstrated what rocket-armed Typhoons could accomplish against retreating enemy forces, Operation Plunder would show their value against prepared defences. Field Marshal Montgomery's plan to cross the Rhine in March 1945 faced an obstacle that had protected Germany's industrial heartland for centuries. The river itself was formidable, 300 to 500 yards wide at the planned crossing points near Wessel. But the real threat came from the eastern bank, where German forces had established interlocking fields of fire covering every likely assault route. Intelligence identified more than 300 anti-aircraft positions within 5 miles of the crossing sites. These ranged from heavy 88mm guns capable of destroying assault boats at long range to rapid-firing 20mm cannon that could shred infantry packed into landing craft. Unless neutralized before the assault began, these weapons would turn the Rhine into a killing ground. Air Marshal Arthur Conyngham, commanding 2nd Tactical Air Force, assigned the counter-flak mission exclusively to his Typhoon wings. Heavy bombers lacked the precision necessary for this work. Their attacks would crater the very ground that Allied engineers needed for bridgehead construction. Medium bombers required clear weather that March's temperamental conditions could not guarantee. Only rocket-armed fighters could deliver pinpoint destruction regardless of visibility. 16 squadrons, nearly 200 aircraft, received individual target assignments. Each anti-aircraft position had its own entry in a catalogue that specified map coordinates, estimated gun type, protective construction, and recommended approach vectors. The campaign would begin 72 hours before the scheduled crossing and continue until every identified position had been attacked. The suppression operation commenced at dawn on the 20th of March with methodical precision. Squadrons operated in rotating cab rank patterns, ensuring constant Typhoon presence over the crossing zones. Forward air controllers embedded with artillery observation posts directed strikes via VHF radio, talking pilots onto targets often obscured by morning mist. Artillery provided smoke markers. Intelligence updates flowed continuously as new positions were identified and added to the target list. Flight Lieutenant James Kyle of 197 Squadron recalled his briefing that morning. A precise grid reference, a warning that the position housed an 88mm gun behind 3 feet of reinforced concrete, and the laconic instruction that it must not survive to see the assault. Kyle's flight approached from the south at 4,000 feet, rolled inverted to acquire the target through the canopy roof. During the dive, and launched at 900 feet, 6 rockets struck within a 10-yard circle. The concrete bunker collapsed inward as warheads detonated simultaneously inside the gun chamber. German anti-aircraft crews discovered that their protective positions had become death traps. Bunkers designed to resist artillery bombardment channeled rocket blast rather than dissipating it. Crews that might have survived near misses from conventional bombs died from overpressure when 60-pound warheads penetrated firing slits or ventilation shafts. By the evening of the 21st, German commanders reported that 30% of their anti-aircraft capability had been eliminated. Replacement crews refused to man certain positions, knowing that Typhoons had their exact coordinates and would return. Morale reports intercepted by ultra-decrypts revealed troops describing the rocket attacks as precision execution rather than combat. German gunners felt individually targeted, their survival dependent purely on whether the RAF had reached them yet on the target list. When Montgomery's troops launched their assault before dawn on the 23rd, the pre-planned rocket campaign revealed its value. Of the 300 flak positions identified before Plunder commenced, post-battle assessment determined that 214 had been destroyed or abandoned. The remainder fired sporadically, their crews shell-shocked and disorganized. British assault boats crossed the Rhine with losses far below planning estimates. Engineers constructed pontoon bridges under harassing fire rather than the predicted annihilating barrages. By nightfall, 30,000 troops held the eastern bank. Montgomery's after-action report attributed the success largely to complete local air superiority achieved through systematic destruction of enemy anti-aircraft defenses. The Typhoons had rewritten the manual for river crossing operations. The accomplishments of the Typhoon squadrons came at a price that their nations are still reckoning with. August 1944, the month of Falaise, cost 2nd Tactical Air Force 131 Typhoons destroyed and 94 pilots killed. These figures represented nearly 15% of total Typhoon strength eliminated in 30 days. Replacement pilots arrived from training squadrons with perhaps 200 hours in their logbooks, immediately thrust into combat, flying 6 sorties daily against targets defended by experienced German gunners. Life expectancy for newly arrived pilots averaged 11 operational sorties. Squadron commanders stopped learning replacement pilots' names until they survived their first week. It was not callousness, but survival. The psychological cost of repeated loss was simply too great to bear otherwise. Veterans developed a detachment that served them well in combat, but left scars that lasted lifetimes. Flight Sergeant Ronald Pottinger later described his first 3 combat sorties as controlled terror. Every flak burst seemed aimed personally at him. Every ground shadow resembled a hidden gun position. Every vibration suggested his aircraft was disintegrating. By his 10th sortie, Pottinger had developed the numbness that separated survivors from casualties. He learned to ignore flak bursts unless they appeared directly in his flight path, to focus exclusively on the target during attack runs, to suppress imagination about what happened to pilots who didn't return. This emotional hardening was essential for survival. It also extracted costs that became apparent only after the war ended. Pottinger admitted in a 1950 interview that he could not watch fireworks displays without experiencing panic attacks. The bright flashes triggered memories of flak bursts that he could not control or suppress. He was far from alone. Many Typhoon veterans struggled with what we would now recognize as post-traumatic stress, though that diagnosis did not exist in the language of the 1940s. The training system that produced these pilots operated under its own pressures. Converting a fighter pilot into an effective rocket operator required a minimum of 12 weeks specialized instruction beyond basic flight training, double the time needed to produce a competent Spitfire pilot. The curriculum extended far beyond learning to fire rockets. Pilots needed to master low-altitude navigation at 300 miles per hour, where a moment's inattention meant flying into hillsides. They studied vehicle recognition using silhouette cards depicting German armor from attack angles, drilling until they could distinguish a panther from a tiger in the half-second glimpse available during a dive. The armament practice camp at Fairwood Common consumed over 8,000 practice rockets monthly during peak training periods. Pilots learned that the weapon demanded counterintuitive techniques. Unlike bombs requiring precise release timing, rockets needed steady aim during the entire firing sequence. Any control input during launch, a twitch on the stick, a rudder adjustment for wind, scattered the salvo unpredictably. Not everyone could master these skills. The washout rate approached 40%. Those who failed were not poor pilots. Many went on to distinguished careers flying other aircraft. They simply lacked the specific combination of reflexes, spatial awareness, and cold nerve that rocket attacks demanded. Those who succeeded paid their own prices. Wing Commander Johnny Baldwin, who would finish the war as the highest-scoring Typhoon ace with 15 confirmed aerial victories plus countless ground targets, flew at least 110 operational sorties in 4 months during the summer of 1944. Some unit records suggest the actual figure was closer to 170. By any measure, it was an extraordinary rate of operations through the deadliest period of Typhoon combat. Baldwin survived the war, but was killed in Korea in 1952, flying F-86 Sabres on exchange with the United States Air Force. He was 34 years old. The principles developed over Normandy fields and Rhine crossing sites in 1944-45 did not disappear when the guns fell silent. Modern close air support doctrine traces its lineage directly to the innovations forced upon RAF Typhoon squadrons by the urgent necessities of combat. The concept of forward air controllers embedded with ground forces, the use of standardized communication protocols, the acceptance that tactical aircraft must operate under ground force direction rather than independent air command, all originated from operations that veteran pilots would have recognized immediately. The cab rank system evolved but never fundamentally changed. American forces in Vietnam operated misty FAC missions with forward air controllers flying low over battlefields, marking targets with white phosphorus rockets for strike aircraft orbiting above. The radio procedures, the standardized brevity codes, even the tensions between air and ground commanders over who controlled the aircraft all echoed conflicts from 30 years earlier. The weapons changed dramatically. Modern precision-guided munitions achieve hit probabilities exceeding 90%, a revolution compared to the 5% direct hit rates that sparked controversy in 1944. Yet the fundamental concepts remain recognizable. Current attack helicopters carry salvos of laser-guided Hellfire missiles beneath stub wings in configurations deliberately echoing Second World War rocket rails. The AH-64 Apache's standard loadout mirrors the Typhoon's arrangement scaled to modern engagement ranges. Pilots still learn to ripple-fire multiple munitions against single targets, accepting redundancy as insurance against mechanical failure or defensive countermeasures. The psychological dimension proved equally enduring. Iraqi Republican Guard units in 1991 abandoned functional tanks after helicopter rocket strikes, behavior that puzzled American analysts until they recognized patterns documented from Normandy. The randomness of survival under area effect weapons creates paralyzing stress regardless of era or culture. Taliban fighters in Afghanistan developed acute anxiety around aircraft engine noise, frequently breaking contact and fleeing when they heard jets overhead, even when those aircraft carried no ordnance. The weapon had changed from cordite-propelled steel to laser-guided explosives. The human response remained constant across cultures and decades. Perhaps the most significant legacy lies not in hardware, but in institutional understanding. The RAF entered the Second World War believing that strategic bombing would win conflicts independently of ground operations. Heavy bombers striking industrial centers, the theory held, would break enemy morale and production capacity without requiring the bloody infantry battles of the previous war. Typhoon squadrons demonstrated a different truth. Tactical aviation, intimately integrated with ground forces, often delivered more decisive results than strategic bombers striking distant factories. A single Typhoon sortie destroying a fuel convoy had more immediate impact on a German armored division than 1,000-bomber raid on a synthetic fuel plant. The soldiers fighting their way through the Norman bocage needed air support measured in minutes, not the months required for strategic effects to materialize. This lesson, learned at terrible cost over the hedgerows and river crossings of northwest Europe, shapes military doctrine worldwide today. Every modern air force trains pilots in close air support. Every army embeds air liaison officers with combat units. Every joint operation assumes that aircraft and ground forces will function as integrated systems rather than separate services pursuing independent objectives. The Typhoon pilots of 1944-45 would understand exactly what their successors are doing. They wrote the manual. In the Imperial War Museum's storage facilities, there exists a logbook belonging to a pilot whose name has faded from public memory. The entries are routine: dates, aircraft serial numbers, mission types, times. But between the lines, if you know what to look for, you can trace the arc of the entire campaign. Early sorties lasting hours, the long transits to targets in occupied France before the invasion, then the tempo accelerating as Normandy consumes everything, multiple sorties per day, brief notes about flak damage, names of wingmen who don't appear in subsequent entries. The pilots survived, most didn't. Approximately 1,000 Typhoon pilots were killed in action between D-Day and the German surrender. Hundreds more died in training accidents, operational mishaps, and the structural failures that plagued the aircraft throughout its service life. Their average age was 23. They flew an aircraft that tried to kill them before they ever saw the enemy. They attacked targets defended by the most experienced anti-aircraft gunners in the world. They developed tactics that no manual had ever described, refined techniques through bitter experience, and passed their hard-won knowledge to replacement pilots who often didn't live long enough to apply it. The German forces they fought called the Typhoon by various names: Jabo-Schreck, fighter-bomber terror; the Panzertoter, tank killer; sometimes simply Der Tod von oben, death from above. The men who flew these missions called themselves, with characteristic understatement, tiffy drivers. They took a failed interceptor and made it into one of the most effective ground attack aircraft ever built. They invented close air support as we know it today. They helped break the German army in France and opened the road to final victory. They deserve to be remembered.